Thank you very much to the organizers for having me. I actually don't know what my name means. I've never been good at that aspect. So what I want to talk to you about today, though, is some recent work we did on quantum effects in enhancing the energetic efficiency of autonomous agents. Big button. Okay, so the backdrop to this talk is very much a little bit like what Jared spoke about this morning. We have an increasing push in society to automate complex tasks. So increasingly, we're delegating things to control systems. That's been going on for a very long time. But we also have smart manufacturing, and we have things like autonomous vehicles, and even most recently, ChatGPT. So increasingly, we're delegating tasks which are extremely complicated to autonomous decision making. And I have some plots here of the energetic footprint of this kind of delegation. So in 2018, I have a Nature article which estimated that by 2030, we would be consuming 20% of the globe's power to power data centers and other such activities. So as we all know, then ChatGPT came along, and I have a revised estimate from, I think, NVIDIA maybe more recently, might have been one of the collaborators. And now we're sort of extrapolating towards maybe the entire global energy supply by 2040, if we keep going at the rate we're going at. So obviously that's going to change. That can't possibly continue at that trajectory. However, what we're going to talk about in this talk is whether quantum technologies have a capability to actually play a role in any case in bringing about this change. So I'm going to give you a very simple toy example or a prototype, which could be part of an answer to this question. So to do this, I need to put in place a framework to work with. And what I do is I'm going to talk about a very general kind of framework. So each time step, I have an agent which is interacting with its environment or a questioner. And it receives an input, stimuli, or question, xt, at the time step, and it responds by producing an answer or an action, yt. And in general, then I specify or delegate a particular target behavior that the agent should actually be able to realize. So that's to say that I write down my desired sequence of future output responses or actions it should take upon any possible sequence of future input questions or stimuli. And I allow its actions or its output responses to be dependent on what has happened in the past. So I'm going to allow my target behavior to be dynamically rerouted or reconfigured on the fly depending on what's happened so far. So this is the most general behavior you could display. And after specifying the target behavior I want the agent to be able to enact, I come back and I ask two questions. The first question is, for this particular target behavior, what's the minimum amount of energy you would have to expend to be capable of exhibiting that behavior? So is there an energetic minimum cost to that behavior? The second question is, since I'm a quantum information theorist, can I get an advantage in terms of can a quantum agent enact the exact same behavior while using less energy than its classical counterpart? So that's my two questions. And to be able to sort of address these, I need to give an embodiment, in a sense, to these concepts. What is an agent? What is an input? To formalize it in a framework. So for me, an agent is always a memory system. I want my systems to be autonomous, responding, but I also want them to change the behavior depending on what's happened in the past. So my agent is actually going to be a memory register which records what's happened so far. In addition, I need to actually bestow my agent with a program. The program which allows it to decide how to make decisions or actions, depending on the input it's received so far. So this program, what it does is it takes in an input stimuli, a tape encoding the input question from that time step. It also takes in an auxiliary tape, thermal tape, which it uses working memory. And then it couples these input stimuli to its memory system, and it actually computes an appropriate output response action while passing the input tape through, preserved. And at the same time, what it has to do is it has to dynamically reconfigure and rewrite some of its memory register to record the outcome of that event, to record what's happened so far in the current time step, so that as this memory and agent propagates forward into the future, it can adapt its actions appropriately depending on what's happened so far in the past. So this is my embodiment. And there's like lots of examples of this. I've written my framework to be completely general so that it can be applied to capture large classes of things. The first example I have here is borrowed from the language of reinforcement learning, POMDP. So here I have a set of belief states, which are the internal states of the agent's memory. And at each time step, the agent gets an input stimuli, an observation from the environment or a perception, and it takes an output action, which is the label of the edge, and hops accordingly into a new belief state. Quantum mechanically, what is an agent? Well, for me, quantum mechanically, an agent is a memory register of a QPU, a quantum processing unit. It's some internal memory state which I have initialized in the QPU, as well as some kind of unitary quantum channel or quantum computational program, which uses this memory to enact it with an ancillary system, which encodes the input information about the input question or input stimuli at that time step. So a quantum agent is some kind of quantum circuit, a quantum program. And then, since I have a concrete description for what is an agent, I know what classes of systems I am looking at, I can now go ahead and I can analyze the energetic efficiency of these agents, the minimum amount of energy they would require to be capable of exhibiting a particular target behavior or doing a specific task I've delegated to them. And to do this, what I do is I take the language of information batteries. So this is to say that I think about a work reservoir of pure qubits in my QPU, which I'm going to need to empower the computation and realize the quantum circuit. This work reservoir couples in to the computation, enabling the physical process. But at the end, the work reservoir of pure qubits is depleted. In general, it's a degraded battery. So then the cost of doing the computation for me is very much the cost of resetting inside the QPU these degraded states. So this is a qubit reset operation. And when I pay energy in my quantum computation, I am actually specifically looking at this type. It's the minimum cost which you would have to pay fundamentally by the second law of thermodynamics, as Felix showed, to enable the computation. Of course, we all know that then practical technologies have other limitations. That's okay. And the main takeaway message from this, though, is that this leads to a concrete equation and circumstance for the minimum energetic cost of executing a particular target behavior of an agent. So I can concretely write down the minimum amount of energy you would need to consume to be able to execute that task. And this minimum energy, I'm sorry, this talk is too short for me to give you the description of all the equations. So don't worry too much about the equation. The important thing to take away from it is that there's two contributions. The first contribution depends on how complex the behavior I want to exhibit is. So this is the fundamental cost of that behavior. Doesn't matter how I realize it, this cost is not going away. It's got to do with the level of complexity of the task you set the agent. It has a term here which depends on the number of different possible actions the agent would have to take. So the more actions you want the agent to be capable of exhibiting, and the more complex you want its behavior to be, the higher the cost at the minimum bound. That's intrinsic, is inescapable, and you're not going to get rid of it. The second term is actually, if you're a physicist, slightly more exciting. We don't really get excited about this term. This is fundamental. This term I can do something about. This says that the agent pays an additional cost, which is proportional to the amount of information it records in memory about the last input question and the last output response it took. So the more the model of the agent I construct records about this last input question and last output response, the more energy it dissipates. And this is heat, actually. This is directly heat inside my processor, so this is heating up your data center. And this I can do something about, because the better the model I construct, the less it retains, the lower the thermodynamic cost, the lower the energetic cost. So the second result we get, that's the first result. The second is that, sorry, quantum agents almost always are more energetically efficient than classical counterparts. So that is to say that if the classical counterpart has two belief states, sorry, Si and Sk, such that no matter what sequence of future questions I ask the agent, I'm unable to infer which of these two belief states the classical agent started out in, purely by looking at the output responses, then there will be a more efficient quantum agent. So that sounds a bit cryptic, but I'll give you an example. My daughter likes ice cream. Doesn't matter whether it's freezing outside and she's wrapped up in a blanket, or if she's sunny and she's at the pool. If you ask my daughter, does she want an ice cream? She'll say yes and go get the ice cream. So if you were to see my daughter eating ice cream, what would that tell you about whether it was freezing or whether it was hot and sunny and she was at the pool? Doesn't tell you very much, right? Because she would have picked ice cream either way. In that case, there's more efficient quantum implementation. And to give you a little bit more of a scientific example, I have here a very quick example of a two-player game. So I have an agent, Alice, who's under interrogation. I have a questioner, Bob. Each time step, Bob is going to ask Alice one of two different questions. I'm drawing inspiration from Blade Runner, so the questions are you human? Question 0. And question 1, do you like electric sheep? To win the game, all Alice has to do is, if she's asked the same question twice in a row, she should make sure her answers agree at both time steps. If in the second round she's asked a different question from the first question, then she just needs to answer at random. She should say yes or no, 50-50 at random. And you can show that to win this game, Alice only needs to know two things about the past. What was the last question asked? And what was the last answer she gave? So she needs to remember the last question because she needs to know whether she's been asked that question again. She needs to remember the last answer she gave because if she's asked that question again, she needs to match that answer exactly. So it's invariable Alice needs to know these two things. If she knows these two things, she can win 100% of the time. All she needs to do is go to this particular diagram, pick the appropriate belief state corresponding to which of the 4 different scenarios she's in, and then she initializes her memory in that state, and afterwards she can always generate the correct responses by hopping on the corresponding edges. If she gets asked question 0, she picks the blue edges. If she gets asked question 1, she picks the white. She emits the answer, which is the label of that edge. 100% of the time she wins. But remember, Alice pays an energetic cost for the number of bits she retains in memory about the last input question and the last output response. And here I'm causing her to store 2 bits. So she'll pay for that. Quantum mechanically, Alice can be a single qubit. So I only need one single system inside my QPU. It still has 4 different states, but I simply choose it to initialize it either spin up or down on the z-axis or spin up or down on the x-axis, depending on the question and answer. And then in the future, I use either measurements in the z basis or measurements in the x basis, depending on the question. It has a quantum program. Doesn't matter. Anyway, the important thing is that it turns out that classical Alice, while storing all of this information in memory, needs 2.5 units of energy per time step to play the game. It's fundamental to her lower bound. She probably needs more because there are other costs associated with inefficiency in the machine, but her lower bound is 2.5. Quantum Alice will only use 1.5. And the classical is already optimal. So that's to say that there's no further improvement possible with classical technology. So the minimum is that you will save 1 unit of energy if you play this game quantum mechanically. Obviously, that's a toy example. I've given you several toy or auxiliary examples, but we can play this in general. And in fact, we get divergent advantage when we play it in general. We can get advantages in which, as the precision grows, we get better and better energy saving. So this is a preliminary example that we might get advantage of quantum processing in the energetics of agents. Okay. I'm probably over time. Am I over time? Yeah. Yeah.
And okay, we have one question.
Thank you very much. Very nice. How fast does it diverge?
Sorry?
How fast does it diverge?
Well, the constant behavior. All the equations, you can, okay. All the equations are behavior that's like the task or behavior you set the agent to directly influences the value of the energy required. So it grows with the precision. The example I'm talking about grows with the precision with which you want a response. We're working in a stopwatch framework, and the precision with which you want the watch to reset and to click. As you scale that precision up, it diverges logarithmically in the precision. So and the classical stays bounded. So the quantum stays bounded. Classical scales up and diverges logarithmically with the precision. But we can generate lots of these kinds of examples. But it's strictly task dependent. You mean the task, I'll give you the cost.
Hi, thank you for the nice talk. So I was thinking, like, I'm not an energy person. I don't do any research on energy, but I was just asking, how do you calculate the energy cost of classical computation and quantum computation? To my understanding, it depends on the hardware that you're using, and how much energy it consumes depend on the hardware. Does not depend. I'm not sure, like, how does you calculate the energy consumption of your agents? And another thing that I wanted to ask is, like, in your slides, you were showing, like, for every input, for every time step that you have an input, you have a. Does it mean you need a new qubit for every time step?
Okay. So the first question, how do I calculate energy costs? Actually, at the moment, we're working at the absolute minimum cost. So fundamental minimum. So we actually work in lambda hours, which is the minimum based on the information. So the change in the state of the processor inherently, the information contained in that state, as you rewrite that information and as you change that information, it's a very fundamental cost you have to pay for rewriting and changing that information. So I look at the state of the processor, computation you have to do, how that changes the state, and then the change in entropy across that computation is a lower bound on the cost of realizing computation. The bound comes from the second law of thermodynamics. As Felix said, we start in the good spot is never is inherently guaranteed. So that's the minimum cost I pay, and that's actually how we get that.
But then there's like maintenance cost of quantum devices. Let's say if we have IBM quantum computer, if we consider that one, the energy to maintain that system just for the maintenance, that's also very high. So do you consider that energy as well?
Okay, so today's quantum technology is generally all in the fridge, right? And a lot of your energy is going into the cryostat, cooling. A lot of energy is going into the control electronics. We do not currently count that. We are not in a model dependent setting. We're in a model independent. We will cover any implementation you will ever see, any neuromorphic computing, any GPU computing, any CPU computing, any quantum device you ever build, it will obey these equations, like as a minimum. So we have the undercut minimum, even if you get it perfect, if you get rid of the cryostat. This is the minimum you'll still pay. I will guarantee you by the second law of thermodynamics, you'll pay the cost on these slides, even once you get rid of all of the inefficiencies. However, obviously, as you add these things, like I wanted the cryostat, I wanted it at 1 millikelvin, you pay extra. I'm not currently counting for that. Alexia will talk to you about that. And I have group members who are literally plugging these things into the wall and counting the energy costs of running them. So we do a second parallel stream of work, which does look into the pragmatic cost of running the cryostat and the rest of it. So those are all overhead costs.
Okay, thank you so much.